All right, let's dive in. Today, we're taking an idea you know really well from basic calculus, slope, and we're launching it into the third dimension. We're going to go from a simple 2D curve to these complex, rolling 3D surfaces. And, well, that creates a whole new kind of problem we need to solve.
I mean, really think about that for a second. For a simple line, there's only one slope at any point, right? But what about a hill? The steepness completely changes depending on which way you're facing. Are you going straight up? Or maybe sideways or downhill? How in the world do we talk about the slope when there are literally infinite directions to choose from?
Well, the really brilliant move in multivariable calculus is to not even try to solve that infinite direction problem all at once. Nope. Instead, we're going to simplify things a lot. We just make one simple rule. We only look at the slope in two very specific directions.
And here's the core strategy. Just imagine you're standing on some kind of mathematical mountain. Instead of wandering off in any random direction, we're going to measure the steepness in only two directions, directly east, which is parallel to the x-axis, and directly north, parallel to the y-axis. That's it.
So this is our first tool, the partial derivative with respect to x. You'll see it written as f sub x, and all it tells you is the instantaneous rate of change, the steepness, of the surface if and only if you're moving in that east direction. Everything else is just frozen.
And you can probably guess what's next. The partial derivative with respect to y, or f sub y, does the exact same thing, but for our north direction. It calculates the slope you'd feel if you only moved parallel to the y-axis, keeping that x-coordinate totally fixed.
Okay, so this is it. This is the most important rule to burn into your brain. When you're calculating the partial derivative with respect to x, you have to pretend that y isn't a variable at all. Just treat it like it's the number 5 or 10 or pi, whatever. It's just a constant. And when you differentiate with respect to y, x becomes the constant. Honestly, this one little trick is the entire secret to getting these right.
So now that we have the slopes in our two special directions, we can start to build the tools we already know and love from calculus, like tangent lines. But this time, they're going to be tangent lines that exist in 3D space, and they follow a really specific, kind of beautiful structure.
Just look at the structure of these vector equations. For the tangent line in the x direction on the left, notice how the y component, y naught, never changes. It's locked in. All the movement is happening in the x and z directions. And then look to the right. For the tangent in the y direction, the x component is fixed. The math itself is perfectly showing us that east/north idea.
All right, that's enough theory. You know the best way to really get this stuff is to see it in action. So let's get our hands dirty and walk through a few classic problems you're definitely going to see.
Okay, first up, a pretty straightforward rate of change question. We've got a surface, we've got a specific point, and all we want to know is, how steep is it right there if we're facing east along the x-axis?
So, step 1, we find the partial derivative with respect to x. In that first term, x squared y, the y is just a constant multiplier, so the derivative is just 2xy. Now that second term, minus 3y to the fourth, since we're treating y as a constant, that whole term is a constant. And the derivative of a constant is just 0. So, step 2, we plug our point 2, 1 into our derivative 2xy. That gives us 2 times 2 times 1 for a final answer of 4.
But what does that 4 actually mean? It means that at that exact point, 2, 1, if you were to take one tiny step in the positive x direction, the height of the surface, z, would go up at a rate of 4. So the slope is positive and, yeah, it's pretty steep.
Okay, next up. This time we need the full equation for the tangent line. We're at the point 1, 1 on this surface, which is actually an upside-down bowl, and we want the equation for the line that just skims the surface as we head purely in the y direction.
Let's break it down. First, we need the full 3D coordinate of our point, so we plug 1, 1 into the function to get z, which is 3. Our point is 1, 1, 3. Second, we need the slope in the y direction. The partial derivative with respect to y is negative 2. At our point, that slope is negative 2. Third, we build the direction vector. Since we're moving in the y direction, the vector is going to look like 0, 1, fy, which for us is 0, 1, negative 2. And finally, we just assemble the line equation. It's our starting point, 1, 1, 3, plus our parameter t times our direction vector, 0, 1, negative 2. Done. You know, this leads us to one of the coolest and most intuitive things you can do with partial derivatives, just comparing how steep things are. If you're on a mountain, you're constantly thinking, is it steeper to go left or forward?
Well, now we can actually answer that question with math.
So here's the setup. We've got a surface and a point. We just need to figure out the slope in the x direction and the slope in the y direction, and then just see which number is bigger. It's a head-to-head competition.
So we do the math. We calculate f sub x, which is 12x squared y squared, and plug in our point 1, 2 to get a slope of 48. Then we calculate f sub y, which is 8x cubed y. Plug in the same points, and we get a slope of 16. The numbers are right there, plain as day.
And wow, when you see it laid out visually like this, it's not even a contest, is it? You don't even have to read the numbers to know the answer. The slope in the x direction, our east path, is just so much steeper than the slope in the y direction. And that is our final conclusion. The magnitude, the absolute size of the partial derivative, tells you the steepness. Since 48 is way bigger than 16, the surface is much, much steeper in the x direction at that specific point.
Okay, we have covered a lot of ground here, from the big ideas to the nitty-gritty calculations. So let's just take a second and boil this all down to the absolute essentials that you need to remember.
So at the end of the day, partial derivatives are just this really clever trick to take a hard problem and make it easy. Just remember, f sub x is your east slope, f sub y is your north slope, and the bigger the number, the steeper the hill. If you can hang on to those core ideas, you've totally got this.
And that leaves us with one last big question. We've totally mastered how to find the slope if you head east or if you head north, but what if you wanted to go in any other direction? How would you combine what you know about the eastward slope and the northward slope to find the slope if you wanted to head, say, northeast? Well, that is the next incredible step on this journey.